Okay, hello everyone. Uh, how are you feeling today? Tired? Okay. Okay, so mostly for today we are going for a little bit notes for the linear differential equations, and maybe if we have time at the end, maybe I'm giving you just a little bit intro for the next techniques, which is the exact equations. Okay. So, and this week, maybe I will give you some homework. Okay, some homework. Maybe I will post on Saturday morning, probably. I think I will give maybe 4 days, 4 days for working on that, so you can optimize your weekend for submitting the homework, or maybe Friday, so that you can have more time, and you can have also time for weekends. You can finish the homework, and you can do other things as well for weekends, right? Okay. All right. Okay. Now to get review, let's just consider differential equations. Okay, this is the equations, and we have initial value 0, 4. Now this is really standard. So first thing, we match up with our px, and we know that this p of x here is equal 1. So we can take the integrating factor. Remember, integrating factor always in the exponent with the power of integral of px dx. Which means we just have this e with power of x. Okay? Okay, and now we multiply this integrating factor to all components in the equations. Okay? And by doing this, the next step is to reverse the product rule. Okay? Remember this as a product rule. So we are going to make out our product form, which include the e to the x and y. And of course, we can integrate both sides. And integrate x e to the x. Do you still remember? Do you still remember how? We can use a partial integration. Okay. Or you can use my method here. So x, maybe using blue. Sorry. This is differentiate, integrate, and then this will be plus minus. So we'll have e power of x y is x e power x minus e to the power of x, and then plus a constant. Okay, and then divide all components by e to the x. So it becomes x minus 1 plus c, and then e with power of negative x, right? So perhaps this is the general equations, and we have the initial value, that is y0 is equal 4. So we are going to put this into our equation. So put 0, and this is 4, this is 0. So this will be 4 negative 1 plus c, or c is equal 5. So we could write the whole solution. So the solution, we say the solution is x minus 1 plus 5 e with power of negative x. Okay, now what I want to explain in this simple differential equations, this solution, remember that our solution is actually has two components, right? The homogeneous one and the non-homogeneous. So we call that this is yc and yp. Okay, yc is when we have homogeneous. Homogeneous is when the right side of the equations of differential equation is equal to 0. Okay, in our example here, if you want to identify which part that is homogeneous and which part is the particular solution, this is particular solutions. Okay, in our equation here, if we look closely, this is our yc, this is our yp. Okay. Okay. Why this is called the yc? So if we look at the general components, that is c e with power negative x. So if we look at the let's say writing the c with power with e power of negative x. Okay. Because this will be equal to 0, or maybe it will getting 0 as x is getting bigger. Okay. So yp and yc, if you want to make sure which one is which, one thing you can do is try several x, and maybe increasing x as larger, and larger. And if you see some part of the component makes a 0, then that will be your homogeneous one. Okay. And the other one is yp. Sometimes the solutions, maybe the whole thing is yc, maybe the yp can be 0, or the whole thing will be yp. Okay. But the interesting here is, if we know that we can have this yp and yc, we can at least make some assumption or predictions what will happen in this solutions. Okay. And we say that this yc, the other name for this part for yc is, we call the transient term. This is just naming. Okay. They are the same thing. Okay? Just yc, okay? But the name is transient term. The transient means that this is what we have here. This means transient. When the solution's getting 0, when we change the variables, the independent variables, we make it larger, it goes to infinity, it's getting 0. Okay, it's getting 0. So we call it transient. So it sounds like it does not really anything. Okay, so it does nothing. Okay, so whatever happens in the components, it doesn't really has significant meaning. Okay. Okay, that's one thing. Okay, about the transient term. So maybe the question is asking, probably one of the questions maybe asking, is there any transient term? Then you can answer with something like this. So you need to imagine one part of the component. Maybe you can make arguments that when x getting larger, this component is getting 0. So you say that, oh, this part is the transient term. Okay. Okay. The next part, okay, what I want to make also notes is in the linear differential equation, we also it's possible to have a piecewise defined function. So you can have two, maybe different interval. So let me give you example. So we have dy over dx plus y equal f of x. This is just a normal linear, right? And we have an initial value. Let's just use 0, 0. And we have another statement that say that this f of x will be equal 1 or 0, depends on the interval. Okay. Now, to solve this, precisely we need to also calculate these two f of x. Okay. And then the solutions will be also piecewise solutions. Okay. So first, if we want to look at the interval, this is going to be from 0 to 1. And this one is 1 to infinity. And of course, if we solve this through our integrating factor method, we get that this will be equal to, I will just skip the process. I believe this is simple enough to see that this will be e power x and y, as the same as the previous example, right? And we see that this is equal to f of x, or let's say we start with 1 first, okay? So we multiply with e to the x. Okay. So we integrate this to get the equations, and then simplify the equations. We get these. This is y equal 1 plus c1e negative x. And then we have the initial value y0 is 0. So we put all 0. So we get c1 is negative 1. And therefore, this is become y equal 1 plus or minus e power negative x. Now this is for the first one here. Okay. Now this is for this interval. So we need to have two solutions, okay? Because we have two interval of solutions. Okay. Now the other solution will be equal to 0. It will be equal to 0. So the other solution, or maybe let's write for x greater than 1, then we will get dy over dx plus y equals 0. In the same way, since it's just 0, we can simplify it easily, right? and we can just integrate, and this will be resulting y equal, let's use C2 for this constant. This will be resulting in this, and we can write down at least we can write down the interval or the piecewise Okay, now the next part is the C2. We still have C2 here that we need to define. So we need to make the functions continuous. So we need to make nodes, need to make the function continuous at x equal 1 to determine C2. So what we are going to do, we are going to take the limit as x approaching 1 from the right, okay, because it's our interval of the functions. Let's write the function y, and the continuity means that this will be equal to the function at that point. Now this implies that C2e negative 1 we plug in is equal with 1 minus e negative 1, or we simply divide by e negative 1. This will be e minus 1. Okay, so it's like in calculus 1. Okay, so we need to make these two statements equal to make continue. Okay, to make the continuity. So because of this, we have this now. Then we can apply to our piecewise. So piecewise becomes, this is 1 minus e negative x. This is from 0 to 1. And this part is e negative 1, e negative x. And x is greater than 1. So we say that this will be continuous on interval from 0 to infinity. Actually, in this linear sections, there are one sections about error function, but I think I will skip for now. So everything that has the error function in the exercise, we are skipping for now. And maybe if we have time later on, we can go back to explain about this error function. Okay, So that's some notes. Okay. Any questions first? So to make out the piecewise, we need to also think the continuity, So we need to adjust the continuity. Okay, let me move to the next section, which another technique we call the exact equations. Exact equations. Okay. So let me begin the exact equation. Okay, let me give you a functions x squared y power 4 plus, let's say, cosine y equal 1. Okay. Let's say we take this a little bit middle. The question or the instruction is differentiate. So before we move going into details about exact equations, I want you to refresh some calculus techniques. Okay, if you still remember how to derive these equations. Okay? So basically, what we are going to do is getting dy over dx equal Okay? That's the goal. Okay? We need to find dy over dx. So this is an intro for the exact equations. Okay. So you can do with partial, or you can just use implicit. Okay. I think just use implicit is, I think, really possible. Right. So we are just taking the dependent variable as y and the independent variable as x. So we are going to differentiate x as usual, and y. When we differentiate y, we need to add dy over dx, right? So let me start this differentiation. So plus cosine y equal 1. So we need to take dx over here. And then from here, we get the x squared y power 4. This will be the product rule. Remember, this is fg, so you will have f prime g plus g prime f as in your calculus. So we will have let's start from 2xy power of 4, right? And then the other part will be 4y, but I will write x first, and then y cubed, and don't forget dy over dx if you try to use implicit. And then for cosine y, we differentiate, become negative sine, and don't forget dy over dx, right? And equal to 0. Let's group all this dy over dx here. So grouping all together, it will be 4x squared y cubed minus sine y, and then dy over dx, and move 2xy4 here go to the right side, and we get dy over dx is equal negative 2xy4 over 4x squared y cubed negative sine y. Okay, done, right? Now, to begin the exact equations, now we have dy over dx here, right? This is differential equations, right? And the question is, can we reverse the process so that we can get our equation at the beginning? This is, well, in our case, in our engineering of math, this will be our solutions, right? This is our solutions. This is our differential equation. So we are going to reverse the process. So that's basically the idea, okay? The exact equations, okay? Okay, probably a little bit weird, but it will be really, really interesting, okay? Okay, let me go to a quick review on what we have learned. Okay, so if we have a function of two variable x, y, let's say it has a constant c, then if you differentiate this, we get the differentials right? We can write our differentials as this. Okay, let's write our functions the same thing as our question here. Where is my question? Oh, here, x squared y4 plus cosine y. Now we can also make out our df. The same thing. And then I'm skipping some process here, but it should be the same component or results. And this is equal to 0. Okay. Now we have nicely an equation that has this dx and dy, right? Or, well, if you would like to rewrite this, we can rewrite this into the previous one, right? But the one that I want to emphasize is maybe there is something in this equation here, this df here. Okay, so let's just play with the questions. Okay? Let's just play with this blue rectangle. So let's just say that there is a question that need to be solved. Solve 2xy power 4 dx plus this minus sine y dy equal to 0. Okay, now remember that we have the f equal to partial f partial x, okay, this part, and partial f partial y dy, right? Okay, now we define this as partial f partial x, okay, and this part is partial f partial y, okay. Okay, now the deal is we are going to have partial f partial x is equal with 2xy power 4, okay. Then try to integrate, okay, so that we get at least f. And then what should we integrate with? Integrate with x, okay, with x. So we add the x here. So we will have x squared y power 4. But does it have another component? Now this is a little bit tricky, but if you see the pattern and if you see how it fits, you will see that there is another components that is a function of y here. Because when you derive with respect to x, y will be 0, right? Okay. 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 Now, let's derive with respect to y, or dy. So dou f dou y, or partial f partial y, and this will be, let me derive one by one. Okay, this will be 4 x squared y cubed. We don't write dy dx because it's not implicit, this is partial, and plus f prime y. Now we have this, okay? Does it look similar with this? Okay. Now so maybe right here, go here. So let f prime y equals negative, right? Sorry. Negative sine y. Same thing, integrate with respect to dy. So we will get fy is cosine y plus a constant. So the function will be x squared y power of 4 plus fy is cos y. Let's just say plus a constant, but we can, because it's a constant, we can just say that it will be equaling to some constant. Okay? Let's say maybe constant 1, constant 2 to make it understandable. Okay. So as an introduction, this is just to give you an overview, okay, that when we have this partials, okay, this partials form, and if we have this kind of structure, okay, the structure here, we have something dx, something dy, okay, and then we take the partial, and of course, later on we are going to see how can we do this equation, what the first step that we need to make sure that this is going to be working. So let me start with the definitions first, and I think maybe, can I check? Okay, but maybe let's just check this, still the same questions. Okay, let's just check. Okay, so let me give you idea how to check exactness. How do we really sure that this function is really our solution? Okay, let's write that f is this. To check the exactness, we are going to see this, and we take the second derivative with respect to y for this dou f dou x, and for dou f dou y, we check with partial of x. Now, dou f dou x is 2x y power of 4, this one here, this dou f dou x. Okay, so this will be dou y 2x by 4. So we just differentiate with respect to y. This will result 8xy cubed. Okay. Now this one we take the derivative with respect to x. The f the y is this one, the whole thing here. Maybe take a longer. So 4x squared y cubed minus sine y. And this will be equal, it's 8x y cubed, and sine y will be 0 because with respect to x. Now when we see this, we know that the equation is exact. Okay, so this is just to give you an overview, okay, before I give you the official wordings and definitions. Okay, now let's move to the official wordings. So a differential expression, usually we write in terms of m x y dx plus n x y dy is an exact differential in region R of the xy plane if corresponds to differential of some function the first order differential equation of this form so the m dx and dy is exact differential is said to be an exact equation if the left side, which means the m and n, the left side is an exact differential. So now the questions, how to make sure that it's exact differential, practically what we did before. We make sure that they both are the same when we differentiate with x and differentiate with y. Okay. So we start with so necessary condition. For this to be exact differential is when we have dou m dou y is equal dou n dou x. Or if we want to make clear what is m, so m, or maybe using a different color. Okay, now when we have this, we say it's exact, okay? Exact differential. So before you deal, like finding the exact, like solving the equation, and you thought that it's exact equation, before doing that, check this first, okay? We need to make sure that they both are the same. If they have the same result for this differential, then you can proceed with the next steps, okay? Okay, maybe a little bit example. Okay. We start with 3x plus cosine okay. Now before solving the equations and finding the solution, finding the y, the first thing you can do is check the exactness. So check the exactness. At first, we identify this to be, let's just say, assume that this is dou f dou x, this is dou f dou y. And then we assume and we differentiate with respect to y for dou f dou x, so this will be equal now this only have y on cosine, so cosine will be minus sine, and this has y over 2, so minus 1 over 2 sine y over 2, and the x will be 0, and the other part is the dou f dou y. Now this part will be negative half x sine y. Of course, I decided that this is going to be just, and it's not the same, right? It's not the same. It's not the same. Well, what should we do now? So we can write that it's not exact, or it's not sufficient to be exact differentials. So then we cannot use exact equations as a method. Okay. Well, if we tweak the equations to make it similar, we can do that. Well, actually, I got it actually from the right one, and then I put it to be wrong. Okay, to just show you that it's not exact. Okay. Okay, I think we can, if I give you this example here, 3x squared plus x cosine y, the x plus negative half x squared sine y dy equals 0. If you try to find the exactness, you will see that they both will be exact differentials. Okay, well, you could like warm up your calculus techniques. Okay, So you need at least the partials. Okay, integrate. I think just ordinary integral, partial. Okay, I think this partial will be very important in our exact equations. Okay, you can check this by yourself. Okay, I believe you can. It will be exact equations. Okay. I think maybe if you would like, we can try some examples. Quite long, equals 0. Okay. The question is to solve this. So the first thing that comes in mind is whenever you have this kind of equation, you have the dx and dy part, then the most obvious way to try to solve is check the exactness. So first check exactness. And let's say this is m, this is n. And then you can try to take this and check the other way around. Okay. I think I would just stop here. Okay. You can continue the exact, and if you want to continue how to find the solution, it's okay. We will continue this in more examples next week. Okay. And maybe I will give you like exercise especially for separable and linear differential equation. Okay. Maybe before we end, any questions first? Okay, if not, then I will ask you in the feedback questions. I'm preparing just two questions. Okay. Maybe it needs at least 5 minutes probably. Okay, I hope you don't mind. Okay. If you want to take notes for the equations, you can take notes or take picture. Okay. Okay, this feedback is mostly two questions about the linear differential equation. I hope you still remember the integrating factor, how to find the linear differential equation, the solutions. Okay. Okay, I will start. Okay. So yeah, for a while. Okay. Okay, let's just start. Okay, giving you 2 minutes. I think it's enough. Don't forget that you need to match the standard form of linear differential equation, which are dy over dx plus pxy equal f of x, right? That's the standard form. So you need to match first with the form, and then you need to find the integrating factor, multiply all with the integrating factor, find the product form, integrate, and then simplify the form, and that will be your solutions. Okay, good. Yeah, I think you need to be careful. Who is Embryo and Snuggles? Okay. Okay, let's start. Okay, just the integrating factor. The integrating factor of differential equation cosine x dy over dx plus sine x, and then multiply with y equal 1. Be careful. Be careful. At least you need to do some integration. But if you remember the result, you can directly go. Or if not, then you need to do some integration. If you forgot, then you can refresh your calculus one. Be careful, again, be careful. You have the ln, so e ln will cancel out with secant. Who's number 7? Okay, good. Okay, finish. Oh, one more thing, the ID. Okay.